So our first speaker is Susan Kassin, and spatial result observations of distant galaxies. First, first results from the GARDEN JWST Space Telescope is slitlet stepping survey.
What is on? Hello? You gotta talk louder. Hi, thanks for joining us. I'm going to wake you up a bit with some observations, completely different. This is easy because this is just explaining the survey. So my name is Susan Kassin. I'm from Space Telescope Science Institute in Baltimore. I'm talking on behalf of the GARDEN survey team. I'm going to explain to you what the GARDEN survey is. It's a survey with Webb. And I just want to point out some of the amazing, important team members. First, I'd like to point out Camilla Petivici at Space Telescope and the students who you'll be hearing from during this conference, Ezra Souquet and Celia Mulcahy. And many other people here, it's a bit of a homecoming for me, are involved in this survey. And I just want to highlight, Joel Primack, who this is, for many of us, a Joel Fest. So coming from the Institute, I'm going to go back to basics and remind some of you who may just be starting that the Space Telescope Science Institute in Baltimore runs these two missions, among others, like Roman and hopefully HabWorld. This is the Hubble Space Telescope, mirror size 2.4 meters. This is the James Webb Space Telescope that we've all been talking about, 6.5 meters. One of the main differences is size. Another one of the main differences is that Hubble works through the UV, through the near infrared, and Webb goes from the near infrared way into the mid-infrared. There are 4 science instruments on James Webb. They're broken up amongst the near infrared and the mid-infrared, and you can tell what they're observing based on their name. I'll be talking about the near-spec spectrograph, near-infrared spectrograph. There's the near-cam imager, takes pictures, and it has prisms. So it is kind of a spectrograph because of the prisms. MIRI, which is a mid-infrared camera and spectrograph, and the NIRISS, which is the near-IR guider. You can ignore all this and only talk about near-spec. Now, near-spec, each of these has its own complex observing modes. Near-spec has something called the micro-shutter array. It allows us to multiplex spectroscopic observations, just like a multi-object spectrograph on the ground. Sandy built Nemotron Tech. This is a similar idea, multi-object spectrograph. However, the implementation is a little different. This is a micro-shutter array. Here it is shown in the lab. It has these 4 quadrants. And here it is shown on the sky, 3.5 arc minutes-ish on the side. Consider it like a screen grid, like the screens in your windows that keep the bugs out. And each little screen, each little hole, you can open and close to create a slit, what we call slit. So this is a section of the deep field, and this is zoomed into this little section. And you can see the observer here placed little shutters across these galaxies. Crystal Martin showed her observations of higher redshift galaxies, where she placed the galaxies in those shutters precisely to get spectra of specific locations on those galaxies. So now I'm going to tell you about the GARDEN program that uses this micro-shutter array in a creative manner. It's a Cycle 1 program observed in September of last year. We used the micro-shutter array like a MOS to observe 56 galaxies between redshifts 1 and 5 in the ultra-deep field. Do 1 pointing with this MSA. We used the highest resolution grading, or RF 3000, so you get spectra of 1.6 to 3 microns. For the experts, it's the G235H grading. 75 hours. No proprietary time. The data have been out there. When we do data cubes, we're going to plan to release them in the spring. Where are we pointed? So for many of you, you know something called the Hubble Ultra Deep Field. It's an area on the sky. HUDF, that's shown here in blue. The images in the background are from what's called the JADE survey with JWST. They have more, but I think this is what's currently public right now. It's reduced. This is the garden survey here. You see it shows the 4 MSA footprints. It also overlaps the SMILE survey, which is MIRI, part of the GCO team, led by Stacey Albert, and the FRESCO survey, led by Pascal Wesch, which is the 444 GRISM, going after high redshift galaxies. So if you are planning a survey, this is a great field to go into. A lot of overlapping data. Happy to work with you and we share data. So the 56 galaxies are distributed on the main sequence as shown. This is star formation rate versus stellar mass. The gray points are galaxies in the candles field. I think it's a magnitude of, they're typical galaxies, so there's just a magnitude cut of about 26. And the red points are the galaxies in GARDEN. This is an increasing redshift from redshift 0.5 to 6. You can see the sweet spot for our survey here is around 2, where that was on purpose. A lot of these galaxies are chosen to be larger. As you'll see, there's a reason for that, and it's to demonstrate with our technique. And here's simply the redshift distribution. You can see that nice peak at redshift 2. We have some galaxies throughout. So this is the slitlet stepping technique. It's not genius. It's simply moving the slitlet step across the galaxy so that we get, instead of just a map of just one part of the galaxy, we get the whole galaxy in there. I named it after an old IFU dither pattern. That's why it has that weird name. Started talking about the Institute, and it luckily kept kind of stuck. I'm hoping to make this a mode on James Webb. I'm trying to make all this stuff publicly available to people to be able to do it. So this figure is a beautiful figure made by Charlotte Welfare. It shows kind of in a cartoon version what slitlet stepping is. So this is MSA quadrant. It's not to scale. It's actually much bigger. These are example galaxies. It shows 8 steps. There are actually 4. You can see bigger galaxies are actually 6. Excuse me. Bigger galaxies get more steps. Smaller galaxies get less steps. But what we do is for the smaller galaxies that are generally fainter, they get less steps, but we stay on them longer. So you can see we shift the MSA configuration over, and then we reconfigure. Shift, reconfigure, shift, reconfigure. All done by hand. And it gets to the point where, goes to the limit where you might have a galaxy that fits in a single shutter, and then we just keep observing that again and again, and it's in every snap. And it is more efficient than the IFU, but the software is kind of cumbersome. We're hoping to release it and make it easier for you guys to use. So when you take James Webb data, please dither it. There's a lot of bad pixels, high RPM pixels. Dither your data. It's not always clear in DADOCS to do it. Talk to me for trouble. So each step is dithered. We do the dance of here. You do a step back, step over, step up and over. I can't do it too well. I'm not a dancer, but you do that 5-point dither pattern on each step. You jump to the next step and you do the dither pattern. Tammy and I were doing it in my office last week. It's fun because you get a lot of, you basically get fresh pixels. There's a lot of snowballs and stuff, so you kind of want to dither it. Plus you get better spatial resolution, a bit better spectral. And then we create data cubes from this. So Jane Morrison is the lead on this. For each galaxy, we have 6 steps, 5 dithers each. This is a fun problem. Jane loves this stuff. We have 30 2D spectra per galaxy, maps into the sky and RA index. There's currently a little something wrong in the WCS, we think. We're working on it, so if you're seeing it, we're going to fix it. And then we take them and both map them drizzle them together to a cube. And we choose, the final, fractal size. And you can do it to many sizes, and we're learning having many sizes is very useful. And because we are going so deep, you really start learning about detectors. And so we've been spending a lot of time ensuring that we actually do go deep by getting our hands dirty and detector stuff. So I don't want to bore you all with it, but I want to give you a heads up of what's going to be implemented in the pipeline. So the near-spec data are only going to get better, especially if you're going for like continuum, right? So we're The primary corrections, we have an improved 1/x correction. We're testing it. Go Russia. It's hard. Improved snowball detection, already in there. Time variable. I live at the institute. Cosmic rays that just kind of get big. We have all kinds of internal names for stuff. Time variable thermal detector bias that we expected, but we didn't expect it that bad. And that fix is in, and we're testing it. We're in the middle of testing that before it goes in the pipeline. And even on road and amplifier patterns, we saw that in the data. It was a little ugly. I think the tests are going to be in the development version soon. Improved DQ mask, flagging high RTN pixels. So the current DQ masks still seem to flag all the, they flag the bad pixels, but not necessarily the high random telegraph rate pixels, which is potentially bad unless you really want to work hard to get them out. And so we're going to fix that we just realized. Mike just realized that. And then improve thermally corrected dark. So this is work done hand in hand, really led by Mike Reagan and Eddie Bergeron at the telescope that are co-eyes on this program. So these effects are on order anything from 0.01 dN to 1 dN. And then we're finally at the point where just on Friday we subtracted some sky and we're like, it got better. Whereas before when we subtracted sky, it got worse. Meaning there was effect. Okay. So now switching back to science, observers, theorists can pay attention again. So we're going to get maps of these galaxies, be able to actually map outflows and winds, gases sometimes in stellar kinematics because we're going deep, metallicity, dusty kineticity with a Balmer decrement, ionizing photons, etc. This is very preliminary. What we do is we do reductions, and then we do reductions of these different corrections, and Ezra Suke has been running and rerunning the pipeline, and we just do it and we try to see, why. So this is a galaxy at redshift 1.9. It's a very odd-looking thing. If you squint, you see this fluff here, blue bit here, potentially dusty red bit in here. We simply just looked at 3 locations, extracted the spectra around sodium D and started seeing some nice absorption, perhaps, maybe, kind of, sort of. So this is very much work in progress. This is that helium-1 line. And then this is sodium D. And I know Crystal Martin and David Chu have done a ton of work on it, so I'd love to talk with you about this, reading your paper. Unfortunately, we can't show more spectra because here we have the detector gap, and here we have the end of the spectrum. But we have a whole spectrum on Ezra. So potential station resolved outflows. And Ezra Suke is going to talk more about that on Friday. Please come to his talk. Really interesting. And then Celia's talking right after me about math. Okay. We have another program that we have planned and executed and have been playing with the data with. We did some cool things in the observing the program that I'm hoping to make more standard on your spec. It's called Meadow. The co-PI is Camilla Pacifici. She's really me and her on all of this, leading it. And then Celia, Ezra, and then the same team plus some theorists on this one. What is Meadow? Meadow is basically GARDEN, but shallower and at different redshifts. So we're aiming for about redshift 3, and we're doing it in the extended growth strip, trying to get more of a sample rather than doing a pilot. And the idea is to, you'll see 6 pointings, about 66 hours, no proprietary time again, and give us a little bit to get those cubes out. The idea with GARDEN, with Meadow, is that we are going to look at galaxy kinematics around redshift 3, and between 2 and 3, plus padded on either end with fillers, and really kind of see what's going on at these redshifts. I don't think anyone's really taken a hard look. Plus looking at spin alignment with the cosmic web, as you guys have taught us, the cosmic web potentially plays a very large role in feeding the galaxy's angular momentum. Many discussions with Charlotte Welker on that one. Hot winds measured from star emission lines, maps the star formation rate, metallicity, so on and so forth. So hoping this would be a nice survey that the community can use and really take to the next level. And so this is, I will just end with this, and we're all tired. and to show you pictures of us planting garden and meadow. And for those of you who know and love APT, you can read our faces here. So thank you so much, and I hope to show you some stuff.
Okay, so we have time for questions.
Yeah, thanks for a nice introduction. I was wondering, using either or both of the surveys that you have planned.
Okay.
Yeah, here. So, would it be possible for me to basically look at this data and check the stellar kinematics of star-forming galaxies down to what kind of stellar mass and out to what kind of redshift? I think for redshift it might be redshift around 2, but I'm also wondering what the stellar mass range would be.
So from our initial calculations in UCSC, we were hoping around redshift 2 and then stacking to higher redshift. Currently we see that in the data, but as we push past all these detector effects, it just keeps getting better. So that is TBD what those limits are once we push past all these detector effects. Yeah, Richard?
Maybe this has been in some various papers published.
No.
Have you? And one question. So when taking the observations, is the alignment good enough on all the slit positions such that it results in a contiguous measurement of the velocity field, or is there sometimes pointing problems with JWST enough that you don't get the slitlets completely, coordinated to be contiguous? And just another question is related. There's been a lot of IFU observations as well of various sources, maybe over the same fields. And my question is, have you compared any of the reductions with basically IFU spectroscopy of some of the same sources? Well, I think also with JWST, presumably you're not going to. I mean, just by accident, it seems like you target some of the same sources.
I think I know what you mean. So for the first question, there's two things at play. One is the target acquisition. There's many things at play. I don't know how complex you want me to get. But there's a target acquisition with the MSATA. And that is, it depends on the astrometry of your input data set, right? So you want to be tied to Gaia, version 3, and if you have that right, if you have that very good, MSATA works beautifully. I'm talking 0.025. It's 5 linear seconds per time. It's very, very fast. The blind offset of JWST seems to be damn good. It is really amazing. But even just, so moving it just one step is like nothing. It can do that, no problem. Even just moving it, like not that, 30, 40 arc seconds off, it's not that bad. You're not going to be crazy off. Depends on where you're pointing. We're here in the UDF, kind of a safe spot. But
you don't end up with cases where there's, where you're trying to do the stepping strategy, and then due to some challenges, there's sort of gaps.
So one challenge could be all of a sudden, because we did 3 visits, right? It's over 24 hours, has to be flipped in 3 visits. So we made sure that our guide stars were the same for each visit, so that it would be the exact pointing to get the same guide star. It didn't observe all of our stuff all in one shot. It did one visit at a time, interspersed with everyone else's observations. So I tried to make sure it was the same guide stars. I imagine it would be also pretty damn good if the guide stars were different. It's my gut feeling. The pointing accuracy on the web is phenomenal. It's been very good. I didn't expect it to be good. I did worry about that for a while. That's why we make sure your astrometry is good. You want to make sure that you have enough stars for MSATA and there's the right brightnesses. And I can teach you some tricks for that. You don't have to necessarily TA this piece of information. You don't necessarily need to TA where you take the observations. I kind of want to bring out what you can do after TA. Got it? Oh, the ISU bit. So I think because of duplications, we couldn't do that. But I would love to compare it. If someone wanted to get an ISU, that would be amazing. You don't overlap. Yeah, I have to. I mean, I didn't want to script too much and do that, but I would love to have an application with the ISU.
So this is kind of a follow-up on Richard's question, but I mean, this is like a beautiful idea, and I'm really like excited to see the results coming out. It seems in detail like really challenging to do. So I wanted to specifically ask. I mean, the individual shutters, their angular size on the sky varies quite a bit over a quadrant. So I mean, you don't have a long slit of one width, but the average size of a shutter in arc seconds varies quite a bit over one quadrant of the MSA. And my understanding is that variation, you know, it's not something you can look up for an individual shutter what the angular size is. That's proprietary information of the instrument team.
Let's talk about that.
Okay.
I know you work closely with Diana and stuff, so
yeah.
Let's talk. I'm
okay.
not sure if that's as bad as maybe I'm.
I think it's a 10%.
Yes. Yeah, I'm not worried about that. But that's just like it's extreme, you know.
Okay, let's thank Susan again.